Hereby the solution of exercise 4.1. So 4.1 is the following function. With height 1. So you see clearly, that's part A, you can see clearly that the period is 2, and that implies that the fundamental frequency is 2 pi, always by definition 2 pi divided by the period, so is pi. So now we will calculate the Fourier coefficients. So first let's start with the general equation. So the kth Fourier coefficient is 1 divided by the period, integral over the period, f of t, so f of t, this function of course, and the periodic function, e to the power minus I k omega 0 t. Quite a mouthful, but. So, the first step what we will do is just plug in what we know. We know omega 0 and we know t, because t is 2. Let's write that here. This is t. Yeah? So we have a half integral from 0 to 2 f of t e to the power minus I k omega 0 is pi t dt. Now we look at this function. You see we have to integrate from 0 to t, but we see basically two different definition areas, one from 0 to 1 and one from 1 to 2. So what is more logical than to split this integral? So we have an integral from 0 to 1 blah blah dt plus half integral 1 to 2 blah blah dt, where blah blah is this. Yeah. Now, as said, and that we see here once more, we see this function is 0 here. So this integral will be 0 because I'm integrating from 0 to 1 over the function which is identically 0. So, now what do I know about the function here? Here I see my function has the height 1. So, what do I get? I get a half, that's this half, integral from 1 to 2, and then 1, because that's the value of the function in this interval, e to the power minus I k pi t dt. So, looking at this, you see that that after some rewriting, you have the integral over an exponential. This is easy. This is a half that was in front, and then it's 1 over minus I k pi e to the power minus a chi pi t 0. So t is 0. No. T is 1. T is 2. But pay attention. Here I divide by a number, but k runs over all integers. So k can be 0. Of course, I want to look at it later, so I say k unequal to 0. And I continue. So this is 1 divided by minus 2I pi k. What do I have? Plug it in. E to the power minus I k pi 2 minus e to the power minus a chi pi 1 is this. So here I have basically calculated the integral for all k except k is 0, but I can simplify this. Note that the complex exponential runs over the unit circle and k is in z. So, since note that k is an element of z, and I set k unequal to 0. But what do I know here? Here I have then e to the power I, 2 pi times a multiple. So this is 1. So this becomes 1 divided by minus 2i pi k, 1 minus e to the power minus I k pi. We look at this one. Just think the complex plane. Here I have the unit circle, here is 1, here is I minus 1. If k is 1, then I'm here. Yeah, I'm here. Minus pi. If k is 2, I'm here. K is 3, I'm again here. So this quantity is minus 1 to the power k. So the only case that we still have to do is k equal to 0. So we look at this, all this solution, and we see where is the first time that we assume that k should be unequal to 0. That's here. So we just continue with that, and so we consider only k is 0 now. K is 0. Now look here. We have, here we can just substitute k is 0. Then we get e to the power 0, that's 1. So we get half integral from 1 to 2, 1 dt. And this is just half. So f0 is 0, f k is, we look, if k is even, then here is minus 1 to an even power, which is 1, so we get 1 minus 1 is 0. So we get is 0 k even, k unequal to 0, k. And if k is odd, then what will we have? This is minus 1. 1 minus 1 is 2 there. And then we have I divided by pi k. K odd. And that's it. These are the Fourier coefficients.